Okay, well, good morning, everyone. My name is Vlad Papangelakis from the University of Toronto, and I have the honor and privilege to be the first session chair of the Iron Control Symposium. It's been 30 years since I was a student, 1986, when I attended the first Iron Control Symposium, organized and chaired by John Dutrizak. This is the fourth in the series that runs every 10 years. And I am confident that this year's organizers, Edgar Pick and his team, have done an excellent work, which you will all enjoy. So we're going to have two speakers in this first session. We are starting with Dr. Mike Collins, whom I know very well, a very good friend. And as an introduction, he has received a doctorate degree from McMaster University in Hamilton, Ontario in '84. And after a brief fellowship visit at the National Research Council in Ottawa, he joined Sherritt Gordon Mines Limited in Fort Saskatchewan, Alberta in 1985. That was 1 year before the first Iron Control Symposium. He became a manager of the Sherritt Research Group in '97, and he is currently, he has climbed the ladder to become the Director of Research in the Division of Technologies of Sherritt International. His work has been involved with lab and pilot plant testing, particularly in the field of pressure hydrometallurgy. He has authored more than 80 technical publications, and he is a holder of 8 patents. He has also a notable community service as a chair of the Hydromet section of METSOC of CIM, and also has been heavily involved in organizing a number of conferences, particularly in pressure hydrometallurgy, over the last 20 years. So without further ado, Mike, I would like to call you to the podium.
Okay, thanks, Vlad. As Vlad mentioned, speaking from Sherritt, we're very much involved in the Ambatovy nickel laterite plant in Madagascar. We're operators of the plant and 40% owners. I'll be talking about the behavior of iron at the Ambatovy nickel operation in Madagascar. Indicate my 3 co-authors here. Let's see, Brett Howgrid, Ed McConaughey, and Glenn Smith. Is that better? Okay. I'll mention Brett Howgrid, Ed McConaughey, and Glenn Smith once again, my 3 co-authors. They've all spent several years in Madagascar during the commissioning and operation of the plant. And in the past couple of years, they've all returned to the Technologies Division of Sherritt in Fort Saskatchewan. And actually, Glenn is sitting right here in the second row. Okay, outline of the paper. I'm going to give a brief introduction to the Ambatovy project and operation itself. Then I'll talk a bit about the process that is used there, and then go into more detail about the behavior of iron throughout the process. Okay, the Ambatovy joint venture, that's the commercial operation. It's an integrated nickel and cobalt enterprise. There's the mine in Madagascar, and the laterite ore is processed through an acid leach flow sheet to produce a mixed sulfide intermediate, which then goes to the refinery adjacent to the pressure acid leach plant. And there's also the marketing arm, so it's quite a large enterprise. all in Madagascar. The feed material, it's laterite, has about 1.1% nickel, about 0.1% cobalt. And this is processed to recover nickel and cobalt metals and ammonium sulfite fertilizer, as well as copper and zinc sulfide byproducts. Design capacity of the plant is 60,000 ton per year nickel and 5,600 ton per year cobalt. Just give you an idea of the location of the plant. This is, of course, Madagascar. The capital city of Antananarivo is this red star. The mine is this yellow square. So it's just north of the town of Moramanga. The actual ore is delivered via a pipeline to the pressure acid leach plant and the refinery on the coast at Tomasina. Of course, Ambatovy is fortunate to be in Madagascar. It's just a beautiful country, well known for different animal species that are there, unique to Madagascar, such as the lemurs. The project itself goes back a fair ways. In fact, exploration at the mine site there started in about 1960 with Malagasy Service Geologique. Phelps Dodge became involved in 1995. Of course, they're now Freeport-McMoran. And over about 6 years, Phelps Dodge at the time did a lot of resource definition, a lot of drilling of the mine site. And they did an environmental assessment and some engineering studies. And really, I'd say the project had a good start with the Phelps Dodge influence, especially with respect to the environmental aspects and the social aspects for the project. And now in 2003, Dynatech signed a joint venture with Phelps Dodge to acquire a part ownership on the project. And Dynatech, for those who don't know, was a short-lived company. Started out as a contract mining company, but Sherritt merged with what was Dynatech International at the time in 1997. The Sherritt International Consultants branch of Sherritt International merged with this contract mining company called Dynatech. And Dynatech Corporation was formed in 1997. So our mandate at the time was to look for projects to invest in, and Dynatech decided to invest in Ambatovy. Then in 2004, the bench scale test work and pilot plant testing was carried out in Fort Saskatchewan, Alberta, at the Dynatech pilot plant. In 2005, Dynatech acquired 100% of the project. And at that time, it was also defined as a project to produce the current design capacity of 60,000 ton per year nickel, 5,600 ton per year cobalt. Also in 2005, we were fortunate to form a joint venture with Sumitomo Corporation and Korea Resources Corporation, as well as select SNC-Lavalin as the engineering, procurement, and construction management company for the plant. And as a result, SNC-Lavalin acquired 5% of the project. Then in 2007, Sherritt International decided to broaden its base for nickel supply and actually reacquired Dynatech, and with that, the Ambatovy project. So currently, we look at the ownership. Sherritt is 40% owner and operator of the plant. Sumitomo has 32.5%, and Korea 27.5%. It was just within the last year or so that Sumitomo acquired the SNC-Lavalin ownership portion. Oops. So here's the next couple of slides show a few pictures of the initial work at site. This is some drill rigs collecting 6-inch drill core for the pilot plant test work in Fort Saskatchewan. And then here's some pictures of the labs in Fort Saskatchewan during the Ambatovy testing days. This is a lab batch autoclave, which many autoclave steps in the process, which we'll get to later. This is the pilot plant autoclave where the ore was processed, essentially the first step of the chemical processing, high pressure acid leaching. This is the countercurrent decantation wash circuit for recovering nickel and cobalt in the solution, washing it away from the leach residue. This is the pilot plant sulfide precipitation reactor that we used to make the mixed sulfide intermediate, nickel and cobalt sulfides. This was the solvent extraction circuit that we used when we did the refinery piloting. So it separates zinc and cobalt from the nickel in solution. And this was the first sample of nickel powder that was generated from those solutions during, so this is the first sample of Ambatovy nickel metal. Here are a couple of pictures of ore preparation pilot work as well. So in 2008, we did a little bit more piloting. The design work was well underway by then, but there was some interest in looking at different parts of the ore body and also confirming the behavior of the ore in ore preparation. So we ran a small ore preparation pilot plant. So essentially this is the feed. The ore, the raw ore, would go up this conveyor into a scrubber after it had passed through a grizzly screen. Then there's two scrubbers, one on top of the other here. This is the thickener to thicken the scrubbed ore. And then the ore that was produced in this pilot plant, we shipped a number of tons of it back to Fort Saskatchewan for one more high-pressure acid leach pilot run. Okay, if we get on to the commercial plant itself, the Ambatovy joint venture, in 2012 was commissioning and startup of the plant, with first nickel being produced in the middle of the year on June 26th. And then we achieved what was called commercial production approximately 2 years later. That's 70% of design capacity, which would have been 42,000 ton per year nickel. And then early in 2015, we reached production, which achieved the financial completion for the project, which is defined as 90% of design capacity for 90 days out of 100. It's a very complicated contract that had just to do with financing of the project. But essentially it means a little over 80% production over a 3-month period. Essentially 90% of 90%. And this chart shows the production at the plant since the first nickel production in June 26. So this starts essentially July 1st in 2012. So quarterly production in tons. And quarterly production of 15,000 tons, of course, would be 100% capacity or design capacity. So you can see the gradual ramp up through the quarters up to we're approximately 80% at the end of 2015. Okay, now I'll talk about the process a little bit. This is the first half, essentially on this slide through to the mixed sulfide that goes through the refinery. So we start with the laterite ore, and it goes through scrubbers and screens right adjacent to the mine. Then there's a slurry of the prepared ore that goes through a pipeline to the pressure acid leach plant on the coast at Tomasina. So it's important to get the right pulp density of the ore so that it has the right viscosity for the pipeline transport, because this is a little over 200 kilometers of pipeline. Then the ore is thickened once it gets to the site to get it to maximum solids content to minimize the water input to the high pressure acid leach. So the thickened ore goes to the high pressure acid leach autoclaves where sulfuric acid and steam are supplied. So it's a sulfuric acid leach at high temperature, between about 250 and 260 degrees centigrade. Then that discharged slurry is partially neutralized with limestone, because there's an excess of acid required to get sufficient kinetics for the nickel extraction in the acid leach step. And that slurry is then partially neutralized before it goes to the wash circuit, which is a countercurrent decantation circuit with 6 wash thickeners. And the washing solution is barren liquor from sulfide precipitation. Then the washed solids go to another neutralization step before it's impounded a few kilometers from site at a tailings management facility. So the recovered solution, which has all the nickel and cobalt in it, and not very much iron, but a significant quantity of iron, significant in that the iron behavior affects all the downstream steps, even though there's only a small quantity left at this point. We'll get into those kind of details later. The first thing we do in processing that solution is to add a small amount of H2S to reduce chrome-6 that is usually in the leach liquor. And if we didn't remove that chrome-6 at this step, it would then react with H2S in sulfide precipitation. And the reaction product is elemental sulfur. And we would not want that in with our mixed sulfide product. It has impacts on the capacity of the refinery. So for that reason, if there's chrome-6 in the solution, and it's monitored with regular analyses, we add a bit of H2S before we go to the second neutralization step. And this neutralization with limestone is to remove more impurities before we actually recover the nickel and cobalt. One of those impurities is ferric iron. So the pH is high enough here to hydrolyze the ferric iron as a ferric hydroxide and remove it from the solution. Then we add the largest part of the H2S to make nickel and cobalt sulfides, which is our intermediate product. Then in the refinery, which is essentially just across the road within the plant site, the mixed sulfide is re-leached in more autoclaves under oxygen pressure. And this is essentially an acid leach, but it's quite low acid, something in the range of 5 to 10 gram per liter acid. So to remove any iron that came over with the mixed sulfides, we have an iron removal step. So we add ammonia to increase the pH, a bit of air to oxidize any ferrous iron, and then we end up separating those iron solids from the solution. These go back to the pressure acid leach part of the plant. They get washed and those solids end up with the rest of the tailings. The solution now has the nickel and cobalt, a little bit of copper, and a little bit of zinc. We go to a copper removal step where it's actually a metathesis reaction. We have zinc sulfide we produce later in the flow sheet. We bring it back to react with copper in solution. So we have essentially our first byproduct here. We use an excess of zinc sulfide, so the copper sulfide that's produced in that step still has some zinc sulfide mixed in with it. But that is a saleable product. Contains the largest part of the copper that was in the laterite ore. Then the solution goes to solvent extraction. The first step is a zinc solvent extraction. So zinc is extracted and then stripped and precipitated with H2S. We have our second byproduct here of zinc sulfide. So the net production of zinc sulfide, that doesn't go back for the copper removal, is a second product. Then the zinc depleted solution goes to cobalt solvent extraction, where cobalt is extracted. It's then stripped, and the strip liquor is contacted with hydrogen gas, again in autoclaves, to make a cobalt powder, which is then pressed into briquettes, so a product of cobalt briquettes. The raffinate has the nickel in it. This is also contacted with hydrogen in autoclaves to make nickel powder, which is pressed into briquettes. And then there's a trace of nickel in this raffinate, which is then stripped with H2S. Similarly, in the cobalt reduction end solution, H2S is added to make a cobalt sulfide, and these are returned to the sulfide leach step. Solution now is essentially ammonium sulfate solution with no metals in it. So this goes to crystallizers to produce an ammonium sulfate fertilizer byproduct. Okay, now we'll go into a bit more detail on the individual steps, especially looking at iron. This is a picture taken at the mine site, so a very simple open pit mining of the laterite. The ore gets delivered by trucks to the scrubbers. The thin slurry is screened at about 0.8 millimeters, so it is suitable for the pipeline transport. Also, we get some rejection of things like magnesium, aluminum, silicon in that screening step. So what you see down here is the composition of the prepared ore. So that's ore that's been through the scrubbing and screening and thickened to about 35% solids to go down the pipeline. So these are the average analyses between 2013 and 2015. So you can see about 1.1% nickel and 44% iron. So the ratio is about 40 to 1 of iron to nickel in the feed. This shows the route of the pipeline from the mine site just north of Moramanga. It's about 220 kilometers, 60 centimeters diameter. And as I mentioned, it's about 35% solid slurry. But the actual percent solid selected really depends on the part of the mine that's being processed. The important aspect is the viscosity of the slurry. Here we see the pressure acid leach plant and refiner at Tomasina. Just down at the corner here is the one of the two ore thickeners at site. So essentially that pipeline comes out of the ground just over here. It gets depressurized and pumped up into these two thickeners. Here we get it to closer to about 40% solids. The thickened slurry goes into one of 5 feed tanks, which feed 5 pressure acid leach trains. Then these are the flash tanks. For that, the flash slurry gets pumped all the way up to this corner of the plant where we have slurry neutralization, which is large stirred tank reactors. Then that neutralized slurry goes to the CCD. So here we see the first of 6. That's CCD1, CCD2, and then there's 4 smaller ones just behind it to make 6 CCD thickeners. The solution then gets taken down to feed tanks here for raw liquor neutralization. And there's 2 parallel raw liquor neutralization trains sitting here, stirred tank reactors again. Those feed these 2 thickeners and 2 solution collection tanks. So this is the neutralized raw liquor, the feed for sulfide precipitation. This is the sulfide precipitation circuit. And the refinery is over on this side for processing that. Here you see the utilities in front. So this is the acid plant, for example. Again, twin acid plants. This is the coal-fired power plant here. So the important part about slurry thickening, the first step in the refinery, is to maximize the solids content of the ore. And this is really for economics of the process. Want to minimize acid consumption and steam consumption in that first step, and also to maximize nickel and cobalt throughput for the plant. Obviously, the less water, the less volume you have, the more nickel and cobalt you can get through the plant of a given size. So the design for the plant is 42% solids. We're more typically getting about 38 to 40% solids in startup. And this has some impact on iron behavior because iron extraction in that first step is really dependent upon the solubility of ferric sulfate in that solution. So if there's more solution coming in, more water coming in with the feed, we have more solution coming out. It also means we have higher extraction of ferric iron, because there's more solution per unit solids. So this is a little bit more detail about the high pressure acid leach. We see essentially 255 to 260 is generally the targets. Sometimes it's closer to 250, but these are generally the target ranges. About 65 to 75 minutes retention time, and a wide range of acid addition, but somewhere around 300 kilos per ton. The nickel is released from the ore upon dissolution of goethite, because there's nickel substituted for iron in the goethite structure. And then that iron is reprecipitated in the autoclaves as hematite. So, which is very important, because in that reprecipitation, sulfuric acid is released. So without that reprecipitation of iron, the consumption of acid required for the nickel extraction would be significantly higher. Now this shows nickel extraction in the plant since the commissioning, end of commissioning in June of 2012. Essentially, design nickel extraction it was for both nickel and cobalt actually is 95%. And here we see the nickel and cobalt on monthly averages since startup in 2012. As you can see, typically it's between about 94 and 96% for both metals. So it's been a very successful part of the operation. Now, I mentioned the net extraction of iron in the high pressure acid leach, dependent upon solubility of ferric sulfate. And that solubility really depends on the temperature in the autoclaves, the retention time, and how much acid is present. So of these things, the temperature and retention time are relatively constant, but the acid addition can be quite variable. And one other aspect of iron extraction is the potential for ferrous iron generation in the autoclaves. Essentially, the ore can be described as reducing if ferrous iron is part of the mix in the product solution. And this generally depends on the ratio of things like manganese, which is in large part there is oxidant like asbolane, manganese dioxide, a ratio of oxidants like that to the reductant components of the feed, such as humic acids. So any carbon in the feed will react with ferric at high temperature in the autoclave step and end up making carbon dioxide and ferrous sulfate as a byproduct of that reaction. So in so doing, once it makes ferrous sulfate, that sulfate is tied up with the iron, and there's only very high limits to what that can be. So the more reductant there is in the feed, the more ferrous sulfate there will be. It's not like ferric sulfate, which is essentially hits a solubility limit depending on the operating conditions. Ferrous sulfate will just keep going up if there's more reductant in the feed. Now this graph shows iron in solution at the plant since early 2013. So this is iron grams per liter. This is the discharge solution from the high pressure acid leach. You can see at times it got quite high in iron, over 18 gram per liter iron. And these spikes really correspond to when we had reducing components in the feed. And you also see in general in 2013 like higher baseline levels of iron. And this is really, we had more ferric iron in solution in the early operation as well. For one thing, the internals were a little different in early operations. So we didn't have as much operating volume in the claves as we do now. So we have longer retention time now, which allows more time for ferric hydrolysis. And we're also getting better at regulating the acid so that we don't have a lot of excess acid around in the claves. So initially you can see quite a bit higher irons in 2013. If you look at 2014 and 2015, the baseline level is quite low. So we're typically in the 1 to 2 gram per liter iron level. And this corresponds to less than 1% extraction of iron. And another thing you notice is that about once a month, we continue to get these spikes where the feed is a little bit reducing, so we're getting ferrous iron in the product liquor. Okay, here, just going to summarize the behavior of iron throughout PAL. We talked a little bit about hydrolysis. In the autoclaves, ferric can continue to hydrolyze and precipitate through the remainder of the flow sheet in PAL. For example, in slurry neutralization, we're adding limestone and increasing the pH. So there is some ferric iron that precipitates from solution here. And again, we hydrolyze a bit more in the CCD because the neutralized solids from raw liquor get returned to the CCD for washing. So there's some neutralizing power in those solids. So there's some further neutralization that happens in the CCD. So there is some ferric that hydrolyzes there as well. Then in raw liquor neutralization, we deliberately increase the pH to about pH 3.7, 3.8. And that hydrolyzes and precipitates the remainder of the ferric iron in solution. So any iron that's left in solution after raw liquor neutralization is ferrous iron. So this solution coming through to sulfide precipitation, then there's a little bit of iron that precipitates in this step, although this sulfide precipitation is designed to make sulfides out of nickel and cobalt, and zinc and copper come along with it as sulfides. A small fraction of the ferrous iron also precipitates under those conditions. Here we see the analyses in solution. I see my time. Got 2.5 minutes left?
Yes, you have.
Okay. So I won't go in detail through these numbers. They're all available in the printed paper. You can see how the nickel to iron ratio increases throughout the flow sheet as ferric iron hydrolyzes and precipitates. It goes from about 2.3 to 1 to almost 10 to 1 by the time it gets to sulfide precipitation. And here, there's actually 2 sources of iron that show up in the mixed sulfide. I talked about the ferrous sulfate precipitating to make ferrous sulfide. There's also some carryover of iron-bearing solids that come through with the solutions. Two sources for that. There's steam from the flash tanks of the high-pressure acid leach are used to preheat the solution for sulfide precipitation, so you can get carryover of leach residue, which is primarily hematite, with that steam. Also, the solution from the CCD can have some entrained leach residue with that overflow solution as it comes forward. So once we look at all the data, it looks like about 3 to 4% of iron in the feed solution is making ferrous sulfide, and then the remainder is carryover solids. Again, these plots are in the paper, but what you can see is iron in the mixed sulfide is the red trace. Target is 0.5% iron. So this line here, so it's frequently below that, or design, I should say. The lower the better, because that iron needs to be handled in the refinery. Every once in a while, as the iron in the feed solution goes up, we see more iron in the product as well. And it's from this data that we get that 3 to 4% of the irons precipitating. This shows, if we use the solution analyses in an iron tie, if we use either magnesium or manganese, we get very similar numbers. This is the average composition of the mixed sulfide, 2015. In the refinery, we've got about, I guess in the sulfide leach, we see about half the iron dissolves there. The other half, which we believe is primarily the hematite that was carried over, does not dissolve, stays with the sulfide leach residue. But the remainder needs to be removed before we get to the other steps in the refinery. This shows iron in solution as we go through. So sulfide leach, it's about 0.34 gram per liter. That's well removed in the iron removal step. It's down to less than a milligram per liter. So now our nickel to iron ratio is close to 100,000 to 1. Then in copper removal, it essentially stays at about 1 milligram per liter or less. As we go through the plant, there's a little bit of contamination with iron, so we actually get slightly higher concentrations in the downstream solutions. This slide shows the overall distribution through the plant. So essentially 99.7% of the iron stays with the leach residue in the pressure acid leach plant. And essentially we've got about 1,000,000 to 1 ratio of nickel to iron. More like about 30,000 to 1 ratio of nickel to iron in solution, which is a change compared with the feed of about 1,000,000. And no trouble achieving a spec for nickel content of the iron. The ratio there is about 22,000 to 1, where LME spec is 5,000. So, gone from 44% iron, 1.1% nickel, to less than 0.05% iron in the nickel product. So, enrichment of about 1,000,000 to 1 in the overall process. So, I'd like to thank Sherritt for allowing me to present the paper. And yeah, thank you for your attention as well.
Thank you, Mike, very well. We can certainly entertain a few questions if you have, which I'm sure you have. If you could please state name and affiliations to improve social awareness.
I'm Price, Hydromet Solutions. Mike, I may not have audibly heard the pH in your iron renewable circuit, in the main circuit. To what pH do you go to? Is that a two-stage counter current operation?
Are you referring to the refinery or the pressure acid leach plant?
After pressure acid leach, after the CCD circuit.
Oh, okay, that's the raw liquor neutralization? Yeah, that pH is about 3.7, 3.8. That's where most of the iron that remains in solution is removed. Yes, 3.7 to 3.8.
And it's sort of it's not a two-stage counter current.
It's one stage, but the underflow solids are recycled to the first of the series of stirred tanks to aid in liquid solid separation. It's one stage for solution. The solids are partially recycled.
Yes, please.
Nick Hazen Research. I noticed that the ramp-up time was about 2 years, and I wondered how that compared to the plan and what effect that had on the return. I mean, is this considered a financial success?
I don't believe it's considered yet a financial success, and mainly because of the price of nickel during the life of the plant so far. So the nickel price would have to be higher before we'd call this a financial success. But the ramp-up time for the 3 years, getting to 80%, that was pretty close to our plan.
Anybody else? Yes, please.
James Bond, University of Queensland. Just with your ferrous spikes that come out, is there any corrective action taken, or is that just kind of goes up and then comes right back down?
Well, we've done a lot of talking about it. What we'd like to, one of the limitations at the mine site is there's not a lot of stockpiling capacity presently. So we don't have a lot of capacity for blending feed. So we know how to bring the ferrous iron down in the leach liquor, and that's the best place to attack it, really, is so it doesn't get into the solution to begin with. It's the cheapest solution anyway. But presently, we don't have the stockpiling capacity at the mine to be able to mix the oxidizing and reducing components well enough so that we don't run into those spikes. So we still hit it about once a month, like I said.
It seems to come right back down, though. It goes up and down. So is that just natural variability?
Well, we're trying for it never to get up, but so we're actually putting some effort into preventing that from happening. We monitor the carbon content and the manganese content of the ore. We try and get the balance right, but without actually having stockpiles of known composition, it's pretty tricky.
Santa Petersburg. I'm just curious, what underflow density did you get with your iron thickener?
Like in raw liquor neutralization, or?
So when you separate out the iron, what's the underflow density?
It's actually well, most of the iron comes out, like 99+% comes out in the CCD circuit. So that's like the hematite residue. So there it's about 50% solids. But we actually are precipitating iron in 2 additional steps. So it's a very small quantity of iron. And in the first one, in raw liquor neutralization, it's really gypsum is most of those solids rather than iron precipitate, and also some aluminum hydroxide. There it's more like about 25% solids at that step, but it really isn't dictated by the iron. It's the gypsum and the aluminum hydroxide.
Mike, I have a question. Pressure acid leach plants sometimes are known to have scaling problems. Do you face such issues?
Yeah, certainly. In the autoclaves, we produce hematite, as I mentioned. We also make allanite in the pressure acid leach process, and there's about 3 or 4% iron in the feed. So allanite is known to make a hard scale under pressure acid leach conditions. So there's a maintenance schedule. What is it? It's about 6 months, 5 months?
7,000 to 8,000 operating hours.
Okay, so could be 5 months then. How many hours in a month?
A little bit more than that.
Okay.
More than 7.5, 8 months.
Okay. Yeah, thanks, Glenn. So yeah, there's a schedule for taking down autoclaves for descaling. At MOA, it's something similar, but the vessels are much smaller. At MOA, they use Pachucas, so the frequency is not near. The frequency of maintenance cleaning is much higher at MOA with the smaller vessels. I think there's a fair bit published on that. Ambatovy with the horizontal autoclaves. Actually, yeah, we can get reasonable operating time before it has to be descaled. But certainly, we make scale in the autoclaves, and it has to be removed.
Okay, I think we have to move to the next. We are running out of time for the next presentation. Thank you very much for interesting. So we are moving to the next presentation. Mr. Masahiro Tanaka is the presenter from Coral Bay. He's a chemical engineer from Saga University in Japan, and he holds a master's degree. His current position is a technical advisor in the production department, and he will be talking about Coral Bay's experience in iron control in the pressure acid leach process.
Good morning, everyone. I'm Masahiro Tanaka from Coral Bay Nickel Corporation. In Philippines, we call CBNC. Today, I will focus on the ion behavior in the high-pressure acid leach process. It's also we call HPAR process. At first, I will introduce our CBNC profile. This is the map of the Philippines. CBNC is located on the south part of the Philippines, around near the South China Sea. And our product is mixed sulfide. Main composition is NiS and COS. Nickel percentage is 56 to 58, cobalt 4 to 5%. And we have 2 plants that is running 1 and 2. Each plant capacity about 11,000 nickel ton and 750 cobalt ton per year. So total capacity is 22,000 nickel ton per year and 1,500 cobalt ton per year. And Sumitomo Metal Mining is the principal investor for the operation and control. And the product of CBNC is shipped to Sumitomo Metal Mining for refining to nickel metal. And this is our process design. The ore nickel ore is fed to the ore preparation circuit to screening to remove the oversized ore. And the ore slurry is sent to the autoclave in H-valve circuit. And it's reached using sulfuric acid. The free acid and some of the ion in the reached slurry is neutralized using limestone slurry before sending to counter current decantation circuit, CCD circuit. And this pre-neutralized reached slurry is washed in CCD circuit using the barren liquor from the sulfurization circuit, like this. The washed reached residue is sent to the final neutralization circuit and the discharge going to tailing dams. The overflow pregnant liquor from CCD, the solution containing the nickel and cobalt, about 4 gram nickel, and additional of limestone slurry, some impurity are removed, and zinc removed in the zinc removal circuit by using H2S gas. The mixed sulfide product is forms the sulfurization circuit by using H2S gas also. The mixed sulfide product is shipped to Sumitomo Metal Mining, Japan for refining the nickel metal. The resulting barren liquor from the sulfurization circuit, the solution after precipitation of nickel and cobalt is recycled back to CCD circuit as a wash water for residue. The excess barren liquor discharge going to final neutralization circuit. This is our overall process flow. Today I will focus on H-valve circuit. So next I will discuss about the impurities control in the H-valve operation. The ore slurry is preheated to 200 before sending to autoclave, and the sulfuric acid is injected to initiate the leaching reaction. The autoclave is controlled at 240 to 50 degrees and 4.0 megapascal, and free acid 45 to 50 GPa. And slurry is depressurized in flush tank and sent to the pre-neutralization circuit. The recovered steam is recycled back to preheater to heat the ore slurry In general, there are several impurities contained in the ore, and they are dissolved in the H-bar process. To give an example, iron in ore is dissolved as a ferric ion and a ferrous ion in the autoclave. Most of the ferric ion forms hematite if temperature more than 200. Hence, the sulfuric acid consumed during reaching is regenerated by the hydrolysis reaction. It's reason that the H-bar process is preferred over atmospheric rating. So the H-bar process is a useful technology for the recovery of nickel from oxidized ore of low-grade nickel. It's also clear that the presence of residual ion in the pregnant rich solution results in increasing consumption of the neutralization reagent. In addition, this also has a negative effect in the downstream process. It's for this reason ion removal control in the H-bar process is an essential item. The oxidation reduction potential, ORP, of the reached slurry has a great impact on the total ion concentration. Generally, the ferric and ferrous concentration ratio depends on the operation ORP, as shown in this figure. The total ion concentration is significantly high at low ORP due to the slip increase in the Fe2 plus concentration. In order to reduce reagent costs and improve product quality, it's important to control the ORP in the autoclave to enhance the ion removal. If the ORP is greater than over 500, the ion 2 plus concentration is reduced. It means we can save on reagent cost. So additionally, this does not cause an adverse effect in the downstream process. Taking one particular example, its effect in the facility filtration facility circuit. So reduced ion concentration make it possible to keep a high operation load, not only cost save. The overall operational load against the installed plant capacity is a numerical value that measures the efficiency of the operation. Anyway, high ORP is better for reagent cost and to keep high operation load. And but the ORP cannot be excessively increasing because high ORP value lead to increasing concentration of harmful chromite 6 plus, like this. So the increasing chromite 6 plus concentration created an abnormal condition in the final neutralization circuit. Since the chromite need to be reduced before disposal to the tailing dams, the concentration of ion 2 plus has been reduced with an including in the ORP operation. But on the other hand, harmful chromate 6 plus including ORP also. So high ORP is required to facilitate the production of hematite. However, in such condition, chromate 6 plus is formed, and this is difficult to remove from the solution. So ORP control is important for save cost and to keep environmental matter. So next I will introduce how to control of ORP in HPAR process. First is the overblend control. And there are three main types of the OR used in CBNC, type A, B, and C. These OR is classified according to their nickel grade. Type A is low-grade nickel, type B is middle, type C is high nickel ore. The main mineral of these ore is gassite, but the components are different for each type. These ore greatly influence the acid consumption and ORP for the HPAR process. And they also influence the physical characteristics of the slurry, such as thickening behavior and viscosity. So defining the ore to be mixed and blending the ore is carried out. The ORP and several impurities are monitored and taken in consideration for ore blending. Adjusting the ore blend make it possible to keep high ORP. However, it's not only the ORP and other impurities need to be monitored. For example, including in magnesium content, including sulfuric acid consumption. So must be monitored. And the next is autoclave temperature control. The ion 2 plus concentration in reached slurry is reduced with including operation temperature, like this. Because of the reaction rate. The ion 3 plus concentration decreases with including temperature. So this suggests that temperature is also very important for improving the equilibrium of the first hydrolysis reaction. So high temperature is better for hematite reaction. And the third is free acid control. Free acid control is also important parameter for hematite reaction. During reaching in the autoclave, impurities are also reached because of this reaction. Excess addition of acid is needed. However, hematite formation is also affected by the concentration of the acid. When the free acid concentration is low, the ion 3 plus concentration is also low. You can see the right figure. This means that the hematite reaction is proceeding. On the other hand, when the free acid concentration is both including the ion 3 plus concentration also including. So it means the hematite precipitation reaction is not occurring. Low free acid is better for hematite reaction. So, however, this is one of the cause of the low nickel extraction. So, determine the optimized raging rate for nickel, and the hematite reaction is required for optimize. Finally, I will discuss about the additional project carried out in CBNC. Aside from nickel and cobalt, CBNC invested for pilot plant for recovery the chromite and scandium pilot plant to enhance CBNC operation. For chromite plant, the chromite is recovered from the ore feed to the HPAR process. The process involves physical separation for get product. Product is Cr2O3 and composed of 41% of Cr2O3 and chromite by ion ratio over 1.2. As for scandium pilot plant, the scandium is recovered from the MS Baren-Rika solution. The process involves recovery of very low concentration from the Baren-Rika by using chemical reaction to get the final product Sc2O3. This is 99.9% purity. Okay, last is conclusion. Today in my presentation, the effect of ion behavior in the autoclave was reviewed. So keyword is adjust the ore blend and the high temperature condition and low free acid condition is better for hematite reaction. So if proceed these, if optimize these keyword, it's possible to save reagent cost and keep high operation load. So CBNC plant design just 22,000 nickel ton per year. But we already achieved 24,000 nickel ton per year in 2014. This is picture after achieving the 24,000 nickel ton per year. That's all my presentation. So thank you for your attention and your time. Have a great day.
Thank you, Masahiro. Very interesting from Japanese experience. Any questions from the audience? Yes, John.
We heard in the Sherritt paper that they have to descale their autoclaves once every 7 or 8 months. How often do you descale the autoclaves at Coral Bay?
Every half year we proceed the scaling in autoclave, but not so hard scaling. Scaling main composite is CaSO4. In case of CBNC, still manageable scaling.
My second question is, how do you produce scandium commercially, and how much scandium do you produce in 1 year? Thousands of tons, I assume. Is that right?
24,000.
How many?
24,000.
Oh. For the scandium, how much scandium?
Scandium.
Scandium, yeah.
Still under discussion. This is still a pilot plant scale, but we have a plan for make a big pilot plant in another factory.
And where does the scandium come out in your process? You must have to reduce the residual iron and then precipitate scandium, or do you precipitate the scandium with the iron?
Scandium is recovered from the Varenlica solution. This is after sulfurization solution, so solution containing low nickel and cobalt. And also scandium is low concentration, ppm order.
Anybody else? Masahiro? Okay, go ahead.
Ivan Kraus again, Hydromet Solutions. I have a question to the zinc removal. I understand how you're doing it, and it's a neat kind of a process, but how much nickel do you still co-precipitate with the zinc, and what do you then do with the zinc sulfide product?
Zinc sulfide PPT, including some nickel percent, but less than 1. Nickel loss percentage less than 1%. And zinc sulfide disposed to tailing dams, sent to final neutralization, and after neutralization, discharge going to tailing dams.
Yes, again.
One more question. I noticed that you take your high-pal solution and neutralize it before the CCD circuit. Some operations, I believe, do the CCD separation and then neutralize the solution. Did you examine both options, and why did you choose to do the neutralization before the CCD circuit?
Okay. Pre-neutralization circuits, this is main purpose. Main purpose is to remove ion 3 plus to injection by using limestone. But after pre-neutralization solution, still remaining some ion 3 plus and other impurities. So we have an additional neutralization circuit for removal remaining impurity.
Sigurd, I have a question on the on your process control strategy. You mentioned it's very important to control redox and acid, and you do that by blending. So I bet you measure both redox and acid in the CCD circuit somewhere. Yes?
Each power plant acid consumption and neutralization reagent consumption depend on the...
No, I understand. Where do you measure is the question.
Yeah. Or stockpile and...
the redox, for example. Where do you make this measurement? And the acid?
We have many portions, but we will focus on the ore prep circuit, thickener underflow slurry. But this is one of the cause of delay action. So we also monitored in ore prep stockpile portion.
So the 500 millivolt threshold that you mentioned, this is a measurement before the autoclave or after the autoclave?
After autoclave.
After the autoclave?
Yeah.
So there must be a very huge lag time from the time you measure until you send the message back to control and readjust the the feed conditions.
Yeah.
So how effective this strategy is?
So we always monitor to our preparation signal underflow 30%, not only reach solution ORP. So before sending to HBAR circuit.
Okay. Any last word? No. So thank you very much, Masahiro.